Hello everyone, welcome to the lecture 3 of this week 2, and we are continuing on discussing the basic radiation fundamentals, continuing from lecture number 2. So in lecture number 2 we discussed about different quantities like flux density, luminosity, intensity. We had a little bit of a difficulty in understanding about the which one depends on the distance and which one doesn't. Okay, but we tried to resolve the issues in the basic concepts of different properties of what is a flux density, intensity, and luminosity, and I hope it helped. We had also given a couple of shown examples worked out, and few also will be there in the subsequent assignment to help you. But even if you're having problem, we can even have some follow-up lectures discussing more on some problems which will clear out the concept. Okay. So now, as we started from the lecture number 2 of this week, that the different cosmic bodies do radiate, emit at different parts of the electromagnetic spectrum, and the closest what it matches is with something called a black body radiation, which kind of is works out for most of the EM radiation that we observe at the radio wavelengths. So a black body is actually an idealized physical object that absorbs all incident radiation across the entire electromagnetic spectrum and emits radiation based solely on its temperature. It does not reflect or transmit any radiation. A black body is often considered as a perfect radiator and a perfect absorber of electromagnetic radiation. The temperature of the Planck block rises faster than the silver block because the black surface absorbs radiant energy from the sun at a greater rate. So if you have seen these two examples of a silver coated body and a lamp black coated body, this temperature rises faster because it absorbs most of the if not all of the solar incident solar radiation than the other silver coated one, which reflects significant amount. So the temperature doesn't rise as significantly as the black body. This is just a close example to show you what black body means. Since absorption and emission are balanced, a material that is a good absorber like lamp black is also a good emitter, and a material that is a poor absorber like silver is also a poor emitter. The spectral distribution of black body radiation is described by Planck's law. It's a very important contribution of Max Planck in 1900. This law accurately predicts the intensity of radiation emitted by a black body at different wavelengths and temperatures, taking into account the quantum nature of the energy levels. What do you mean by quantum nature? We have read in quantum mechanics that that energies are quantized, okay, and it doesn't necessarily have a continuous flow, but they're quantized in terms of h nu. So the minimal packet of energy is h nu, where h is the Planck's constant and nu is the frequency of the emission. So Max Planck proposed that the energy of electromagnetic radiation inside a black body is not a continuous, but instead comes in discrete packets of quanta of energy. The spectrum of the radiation emitted by hot opaque objects can be fit by a model that assumes quantized units of energy. The primary law governing the black body radiation is the Planck radiation law. Planck used the quantization of energy. En is equal to n h nu, where n is the level. Planck used this quantization. It gives the intensity of radiation emitted as a function of wavelength for a fixed temperature. So we have these two formula, the B nu, the spectral radiance as a function of time temperature, the capital T, is given by 2h nu cube over c square, then 1 over e to the power h nu kt minus 1. That's the Planck function. Nu is, of course, the frequency of radiation, and T is the temperature of the body. Okay, if we write it in terms of the wavelength, we get B lambda T is equal to 2hc squared over lambda to the power 5, then 1 over e to the power hc over lambda kt minus 1. Okay, K is the Boltzmann constant, H is the Planck's constant, and C is the speed of light. The T is the absolute temperature of the black body in terms of Kelvin. And lambda is the wavelength of radiation, so does nu. So that's the Planck's law. Now, how do we see this? If you plot this, look at the right hand side curve first. If you look at the brightness, the B nu, in the units of watts per meter square per hertz per radian square, you see that this is kind of a continuous curve as a function of different frequency. The wavelength decreases in this level and the frequency is increasing towards the right, and wavelength is increasing towards the left. So you see, as the temperature of the black body actually rises from 1 Kelvin to 10 to the power 10 Kelvin, what significantly you can see, the peak is moving towards lower and lower wavelength or higher and higher frequency. Okay, that's quite significant actually. So if as the temperature rises, the peak in this emission spectra actually shifts from radio to submillimeter to ultraviolet, optical ultraviolet, and so on and so forth. It goes to higher and higher frequency. So it moves from radio to gamma rays in some sense as the temperature goes higher. The same is actually taken into this particular plot on the left hand side. If you see, there is ultraviolet, visible, and infrared, and as the temperature goes, the peak of this location goes from infrared to visible to ultraviolet slowly and slowly. So that's a very significant result of this Planck's law. That kind of gives you an understanding that the maximum value, the maximum wavelength, the wavelength at where this spectra actually peaks, that and the temperature kinds of have a inverse relationship. As the wavelength decreases, as temperature increases, the wavelength at which the spectrum peaks actually decreases. This actually is given by this famous law called Wien's displacement law. We will be coming in a bit. So that's the whole power of the thing. So that also gives, like, as you move to the more higher and higher in frequency, the temperature also increases. So the spectrum peaks at a higher and higher frequency with the temperature of the black body constantly increasing. Python has become very famous, so we have given a small code for you to play with. It will be in this particular slides that we share with you. Thanks to the TA, we have put in a short to this thing, so you can basically play with this Planck function, which we have defined over here, and if you can just keep plotting with the constant of temperature, so you can do it by yourself and see how this thing matches, and also kind of you can connect the maximum value of lambda max for each temperature, and you can see yourself the development of Wien's displacement law. So Wien's displacement law, we know that this lambda max, or the value of the wavelength where there is a peak for the black body spectrum, is called lambda max. The wavelength at which the black body radiation becomes more intense, or the most intense, is the lambda max. T is the absolute value of temperature for the black body, and B is the Wien's displacement constant, which the value of that is 2.898 10 to the minus 3 meters Kelvin. Wien's displacement law, so that is linked by this lambda max is equal to B over T, or lambda max times temperature is a constant. So Wien's law is essentially an understanding the spectrum of electromagnetic radiation emitted by objects at different temperatures, such as stars or other astronomical bodies. It played a crucial role in the development of quantum mechanics and our understanding of thermal radiation. So this is again a bit of explanation. As say for a star which has a red star of 4000 Kelvin, um, the peak is near the infrared. For a white star like our sun with 5270 Kelvin, the peak value occurs in the visible range. For a blue star, sorry, peak value, yeah, for a blue star of much higher temperature, peak value is almost peaking near about from visible to ultraviolet. And so as the temperature of the star becomes hotter and hotter, the peak slowly shifts from infrared to visible to ultraviolet in this way. Great. So I think this is another short snippet of Python code you can start playing with. It will be available in the handout. Another important law in this context is the Stefan-Boltzmann law. It is actually a fundamental principle in physics that describes the total radiant energy emitted by a perfect black body per unit surface area. It quantifies the relationship between temperature of a black body and the rate at which it radiates the energy. Stefan-Boltzmann's law states that a black body radiates electromagnetic waves with a total energy flux E directly proportional to the fourth power of absolute temperature of the black body, or E is proportional to the power 4, where T is the absolute temperature. And if you put on the proportionality constant, the sigma is called Stefan's constant, or it is given by 5.67 10 to the power minus 8 watts per meter square temperature to the power 4. So that's the entire Stefan-Boltzmann law. And we can also derive it from the Planck's law itself. So we go back to the Planck's this spectral radiance function, B nu function of temperature, capital T, is 2h nu cube over c square and 1 over e to the power h nu k over kt minus 1. This is the Planck's law. So if you integrate over all values of frequency, then you essentially end up in this integral. You replace the h nu over kt by x by substitution, and then you essentially end up with the integral which is x cube over e to the power x minus 1, integral of that from 0 to infinity, which comes out to be pi to the power 4 over 15. If you replace that, you finally get something like the bt is equal to sigma t to the power 4, where sigma is given by this 2 pi to the power 4 k to the power 4 over 15 c square h cube. This is Stefan's constant, which comes out to be 1.8 10 to the power minus 5 ergs per centimeter square per second per temperature K, Kelvin inverse to the power 4. So this is another way to derive Stefan-Boltzmann from the Planck's law. What are the applications of this law in astronomy? Luminosity of the star. The Stefan-Boltzmann law allows astronomers to estimate the total luminosity of stars on their observed radiation by measuring the flux energy, which is energy per unit area per unit time, received from a star, and knowing its distance from the Earth, astronomers can estimate the total radiant power or luminosity. So if you know the temperature, you know the flux. And characterizing exoplanets. When studying exoplanets, the Stefan-Boltzmann law is used to estimate their temperatures and hence classify them as hot Jupiters, warm Neptunes, rocky planets, or other types of planets based on their emission characteristics. So this is exoplanets are basically the planets which are not in our solar system but outside. So there's a huge kind of an expedition to understand, are we the only intelligent people in the universe? They're only inhabited by the Earth, or are there there are other intelligent form of life existing in other parts of the universe. You know, intuitively it is not absurd that to imagine that there should be multiple such cases. Just Earth cannot be just the only one, and so there is hunt for other exoplanets, maybe the same distance from their star, and having able to retain their atmosphere, so it's conducive to have life in a normal form, like single cell organism, to up to intelligent form as good as human beings. So that particular quest ended up trying to choose the right kind of exoplanets for which in which the life is possible, and that's a good quest. And so Stefan-Boltzmann law, even as basic as this, has a role to play in understanding those results. In stellar radii, by combining the Stefan-Boltzmann law with other observational data such as stars' distance, apparent brightness, spectroscopic information, astronomers can estimate radii of the stars, providing insights into their sizes and evolutionary states. Cosmology and early universe, Stefan-Boltzmann law plays a crucial role in understanding CMB radiation, which is the afterglow of the Big Bang. The law helps in determining the temperature of its radiation, which is crucial for understanding the early stages of the universe. There are lots and lots of applications. The next in the line is Rayleigh-Jeans law. It's actually a limit to the Planck's law, and we'll show you how it works out. But it is a classical theory that describes spectral radiance of black body radiation at a given wavelength for low frequencies. Law was proposed independently by Rayleigh and Sir James Jeans in 1905. Rayleigh-Jeans law attempted to explain the spectral distribution of thermal radiation emitted by a black body, which is an idealized object that perfectly absorbs and emits all radiation incident upon it. According to classical physics, it was assumed that the energy radiated by a black body is proportional to the temperature of the body and the frequency of the radiation. It highlighted the limitations of classical theories and the need for a quantum mechanical approach to accurately describe the behavior of the black body radiation at all wavelengths. Now, how we derive Rayleigh-Jeans law from the Planck's law? So Planck's law, we go again back to the spectral radiance function, which is given by this by the one in the bracket, and we note that if you have h nu over kt very very less than 1, or h nu is very very less than k times t, then actually you can expand this in terms of series, exponential series, and you can retain only the first term instead of all the terms. So e to the power h nu over kt will become 1 plus h nu over kt, and there is a denominator, there is a -1, so 1 goes away with the other one, and h nu over kt remains only in the denominator in the Planck's law. So if you put this into there, you finally get the spectral radiance function under the RJ limit, or the Rayleigh-Jeans limit, as 2 nu squared over c squared times kt. That's a very powerful derivation, because now you have a quantity, spectral radiance, which is almost like an intensity, is proportional to just the temperature of the black body. Okay, and so that's which slowly will give rise to something called a brightness temperature concept. Anyway, before we come to that, we just show the other form of the Rayleigh-Jeans law in terms of lambda, so that is 8 pi kt over lambda to the power 4, and just to know how this translates in actual reality in terms of number. So what is the limit? Like, for example, what wavelengths or what frequencies qualify to be in the Rayleigh-Jeans limit and what doesn't? So in order to do that, understand that, because that's a very powerful number for observers, h nu over kt will finally translate into nu in terms of gigahertz, which is less than 21 times T over K, T in Kelvin. Okay, that's the number you look for. Safely we can say it works below 5 gigahertz. As you go above 5 gigahertz, we have to check and see if it is still applicable. It may be some secondary order correction on top of that. So B, this in this entire thing, B is the spectral radiance of black body radiation, K is the Boltzmann temperature, T is the absolute temperature of the black body, and lambda is the wavelength of radiation. So yes, I think there is another interesting plot where you can plot both Rayleigh-Jeans limit and the next Planck's function in at the same time. And this is a snippet of the Python code which you can use. So that brings us to this definition of something called brightness temperature, which is extremely important. There are lots of temperatures will be coming in our discussion throughout this course. This is the first one, which is the brightness temperature after the black body temperature. And we will have antenna temperature, sky temperature, noise temperature, etc., etc. This is a whole course where we will talk at one end about intensity, flux density, on the other side different temperatures qualifying different objects. Sometimes the sky, sometimes the physical object, sometimes the some parameters and system. Okay, so Rayleigh-Jeans limit said that this is the BRJ, and which is 2 pi 2 nu square over c square times kt. So if you just keep rearranging those matters, you will finally see that the T, which is now considered as the brightness temperature, so T sub B can be written in terms of lambda square over 2k times I nu, which is the specific intensity. Okay, so that's also can be mentioned here in terms of nu and the lambda both. For a source with a flux density S nu, this can be written in terms of the brightness temperature as well as the size of the object. So if you keep writing this in terms of the flux density, so flux density in Jansi can be expressed as 2.65 times brightness temperature in Kelvin, of course, over this the extension of the source in theta in arc minutes square, and then lambda over in lambda to the power minus 2 in terms of centimeter. Okay, so this is the very useful tilt. So we have the spectral radiance in the RJ limit, Rayleigh-Jeans limit, that is proportional to the temperature and nu square, and from there you will define the brightness temperature in terms of specific intensity I nu, and especially both in terms of lambda as well as nu, and then from there derived what the flux density will look like for an extended source. So that's the final formula given over here, which is very, very useful to, if you have an extent, then what is the relationship between the source, the brightness temperature of the source, and the flux density. This will keep coming as we move forward. So the next topic of today's discussion is radiative transfer, and this is how the electromagnetic radiation propagates through a medium. And so supposedly this is a source, towards the left it's a star, for example. It passes through our interfering medium before it reaches a detector, which can be also a telescope or your eyes. So while it goes through this extended medium, it can be interstellar medium, it can be interplanetary medium, it can be intergalactic medium, intercluster medium, whatever. I mean, the space, any space, which can be even vacuum as well as filled up with plasma or other materials. This radiation can suffer absorption and also emission from the medium itself. So how do we take care of that while understanding the incident radiation which we detect, and finally the actual radiation which actually comes in. So from the observed radiation we have to decipher the actual radiation, and that will only happen if we know about the intervening medium and the different characteristics of the intervening medium. And sometimes either we know the background source well to use this principle to actually characterize the intervening medium. Sometimes we know the intervening medium well to be able to know to decouple this effect of the intervening medium and to understand what the actual radiation is. You can use it in both ways. Alright, so radiative transfer itself refers to the process by which electromagnetic radiation interacts with and propagates through a medium. Okay. Electromagnetic radiation can be absorbed, scattered, emitted, or transmitted as it interacts with the particles and molecules present in the medium it travels through. Okay. The behavior of the radiation depends on factors such as properties of the medium, density, composition, the wavelength of the radiation, and the temperature of the medium. So in astrophysics, the radiative transfer is fundamental in understanding how light from stars and celestial bodies travel through space, interacts with the interstellar dust and gas. It helps astronomers to infer properties of the stars and galaxies and other astronomical bodies. So the different kinds of emission, the thermal emission with blackbody radiation we have already discussed. There are non-thermal emission like which are non-blackbody in nature, and a process by which a material or object emits electromagnetic radiation such as visible light, infrared radiation, or radio waves. Emission can occur due to thermal variation, particle-particle interaction, and particle field interaction. Emission can broadly classified into two categories. Thermal emission, as we said, the black body mostly, it happens due to thermal energy of a material or object, and non-thermal because of different astrophysical processes. It often is associated with high energy phenomena such as synchrotron radiation, and so and so. So essentially non-thermal processes are also there, but whatever be the process of emission is, they can change. So typically we know that the lower frequencies, the non-thermal radiation of synchrotron is the most dominant, and as we go to higher frequencies, say above 3 gigahertz or so, thermal radiation, mostly of the dust, takes over, and then finally it also turns over and near above X-rays. So we will come to the actual emission processes more more rigorously towards the end of this course. So right now you just understand that there is an emission which can definitely happen from the stars itself and also from the intervening medium. And the actual emission from the stars or other cosmic sources, they can travel, and so they are incident on intervening medium, and it finally goes through the processes of absorption and emission, and then comes out from the other side of the medium after being affected by that. So how do we go about defining all this? So emission is defined by the emission coefficient J nu, which is kind of if we have the intensity of the radiation, so the rate of change of that is given by this emission coefficient. Okay, and so the transfer equation in totality can be written as di nu ds is equal to minus kappa I nu plus J nu, where J is the emission term coefficient and K is the absorption coefficient, as you will understand. So if a system is in full thermodynamic equilibrium at temperature T, then di nu ds is equal to 0, and I nu is given by this spectral radiance function B nu, which is function of T. So rearranging the radiative transfer equation, it is we get that di nu ds is equal to 0 is given by kappa beta nu plus j nu, which is then rearranging that, you get the spectral radiance function as a ratio of j over kappa. This is also called Kirchhoff's law. So absorption, a process by which a material or a medium absorbs electromagnetic radiation incident upon it. When radiation interacts with a material, some of its energy is absorbed by the material, leading to an increase in internal energy of absorbing medium. It is closely related to the material's properties and wavelength of the incident radiation. Different materials have specific absorption characteristics, and absorption behavior can vary significantly across the electromagnetic spectrum. Have significant implication in various fields including astronomy, atmospheric sciences, remote sensing, and spectroscopy. Applications for absorption are absorption lines and bands in spectra are important tools for identifying chemical composition of the celestial bodies. Objects, for example, in stellar spectra, dark absorption lines are caused by absorption of specific wavelength of light by element present in the star's exterior layer. So, if we want to define the absorption coefficient, then it is given by dPds, or the infinitesimal probability of a photon being absorbed in a thin slab of thickness ds is given by kappa. So for a absorption only case, this di nu over I is given by minus kappa ds. So that gives you something like I nu, if you go from the S in to S out. So if you when you come into the medium, you have if you come, when you are coming in the incident ray, it is S in, and when you are going out, it is the S out. So the effect of the intervening medium is from between S in and S out. So then this integration should also be within S in and S out. Okay. So that defines the intensity at S out minus intensity at S in. Logarithm of both of that is equal to minus this integral kappa S and ds, where S varies from S in to S out. So if you rearrange that, you finally get that your I nu at the final end when it comes out of the medium over I nu when it was coming incident is given by exponential of minus tau, where tau is given by this integral of kappa S of times ds, which is also referred to as the optical depth of the medium. So that's the definition. So basically, your incident and the outgoing intensity is affected by the optical depth, which kind of makes sense. So if it is optically thick, nothing almost comes out of the other end, and it's optically thin, then nothing happens to the incident radiation, both are equal. So the next thing is we can talk about the thermodynamic equilibrium at which we are making all these assumptions of di nu ds equal to 0. It's a state in which thermodynamic systems is balanced and stable with no net exchange of macroscopic properties such as temperature, pressure, and chemical potential between its different parts. Thermal equilibrium refers to a state in which two or more objects or systems are at the same temperature and no heat transfer occurs between them when they are in contact. In this state, the net flow of heat between the objects is zero because they have reached a balanced distribution of thermal energy. If a medium is not in thermal equilibrium with its surroundings due to the rate of energy absorption and emission is not balanced, leading to changes in the medium's temperature. Of course, if you have a thermodynamic equilibrium or thermal equilibrium, then there is no heat exchanges with the surrounding. Okay, so it has reached the equilibrium, that's called. If not, then there will be some exchanges happening one way or the other. If there is complete equilibrium of the radiation with its surrounding, the brightness distribution is described by the Planck function. which depends only on the thermodynamic temperature of the surrounding. So we are reiterating that the Planck's law is the black body radiation is valid in thermodynamic equilibrium. If there is still some exchange going on, that is not the value. So often we define something local thermodynamic equilibrium, that it may be true locally between the object and its immediate surrounding, may not be valid for the global situation. So for an LTE or local thermodynamic equilibrium, the following assumptions should hold. Uniform properties, that is the properties of interest such as temperature, pressure and chemical composition are assumed to be nearly constant throughout the local region. No macroscopic flow, there is no macroscopic flow of matter energy within the local region. Any transport process like heat conduction, diffusion occurs at much smaller scale and time frame compared to the region of interest. So at the large scale, there is nothing happening, all happening within very small boundaries. Rapid interaction, that interaction and collision time scales of particles within the region are much shorter than time scales over which the properties of interest are changing. Equilibrium reactions, chemical reactions in local region are assumed to be in equilibrium, meaning the forward and the reverse reactions occur at the same rate. Full thermodynamic equilibrium will be realized only when very special circumstances, such as in a black enclosure or say in stellar interiors. Often Kirchhoff's law is applicable independent of the material, and as is the case for complete thermodynamic equilibrium. So Kirchhoff's law gives that the E nu, epsilon nu, which was actually J nu earlier, over kappa nu is equal to the spectral radiance function. In general, I nu, which is a specific intensity, will be a little bit different than B nu. If we define the optical depth as in the figure, we have just defined it earlier also. So that is the kappa nu ds from S naught to S or S in to S out, and that is given by this particular quantity. So you can write down the equation of radiative transfer in terms of now tau nu. So instead of writing it in terms of S, you are writing it in terms of tau nu. So how to do it? You have di nu ds is equal to minus kappa I nu plus epsilon nu, or it was J nu earlier. So you can just divide the both sides by minus kappa nu, and you get on the left hand side minus 1 over kappa nu di ds, which is nothing but di d tau nu. You get on the right hand side I nu from the first term, and the second term is actually spectral radiance, or B nu. Okay, so if you take take the integration from both sides, you finally end up having this I nu at S is equal to I nu 0 e to the power minus tau nu plus this integral of B nu times e to the power minus tau. Okay. So yeah. So this, if you can finally compute this, you finally get that this full radiative transfer equation is I nu S is equal to I nu 0 at the incident times e to the power minus tau nu S plus B nu T into 1 minus e to the power minus tau. Okay. So for large optical depth, that is for tau nu 0 goes to infinity, the I nu is basically the B nu. Okay. So it is just the emission from the intervening medium. It is not nothing from the source actually travels to that, because everything gets absorbed. The observed brightness I nu for optically thick case is equal to the Planck blackbody brightness distribution independent of the material. If the intensity is to be compared with the resultant obtained in the absence of an intervening medium I nu, we have this expression. So now we do have the optically thick case and optically thin case also we will discuss. So the radiative transfer equation finally is of this nature. Di ds, which s is the line of sight propagation, is minus kappa nu I nu plus epsilon nu, where epsilon nu actually is the emissivity. So if only absorption, emission only, kappa is equal to 0, so it goes to this level. And for absorption only, then it takes the value of a to the power minus tau, where tau is given by this integral of kappa times ds. Now, if I replace now in Rayleigh-Jeans limit, if we replace the brightness temperature with the replace the specific intensity with the brightness temperature, then we end up having the radiative transfer equation as this: Tb delta dTb d tau is equal to Ttb s minus Ts. If we do that finally we arrive in this radiative transfer expression, which basically replaces the I with the T essentially. So you have the same tau which keeps carrying on, and you finally end up in this radiative transfer equation where Tb, which is the brightness temperature when the radiation comes out of the intervening medium, is equal to the incident radiation brightness temperature multiplied by the e to the power minus optical depth, and then T of the medium times 1 minus e to the power tau nu. Okay. For optically thin case, Tb results into tau nu times capital T, and optically thick case, it is just the T of the medium. Great. So I think we have tried to squeeze in mostly the discussion with regarding the black body radiation, Rayleigh-Jeans limit, and now the radiative transfer. It's a bit maybe faster, so we'll see with a couple of example questions how to make it more explanatory. So let's look at some of the example questions. A star emits most of its radiation at a wavelength of 450 nanometer. Use Wien's displacement law to calculate the temperature of the star. So the wavelength, we know the lambda max equals to B over T, where B is the Wien's constant. And so if we know the maximum wavelength is 450 nanometer, then given the value of B, we can calculate the value of the capital T as 6444.3. Our next question is a metal surface at a temperature of 5000 Kelvin emits thermal radiation at a frequency of 1 terahertz. A terahertz is 10 to the power 12 hertz. Calculate the spectral radiance B nu according to the Rayleigh-Jeans law. So, if we write it down, the spectral radiance can be equated in terms of the temperature of the black body, and also the frequency. So if you put all those values over here along with the proportionality constant, you finally get the value of the B as 92 times 10 to the minus 4 watts per meter square per steradian per hertz. The next question we have: a star has a temperature of 10,000 Kelvin. At what wavelength does this peak spectral radiance occurs according to Planck's law? Now, according to Planck's law, the peak spectral radiance occurs at a wavelength alpha peak when the exponential term e to the power hc over lambda kt becomes equal to 1. So lambda peak is equal to this, and given by this quantity of 4.5 10 to the power minus 7 meters. So basically you follow the Wien's law. An object with a surface area of 3 times 10 to the power minus 4 meters square is observed to have a total power radiated of 5 times 10 to the minus 3 watt at a certain temperature. Calculate the effective temperature T of the object according to Stefan-Boltzmann law. So the surface area is given, total power is given, so we calculate the effective temperature. So we know that for Stefan's Boltzmann law, the temperature is given by P total. So P total actually is sigma A times 10 to the power 4. So T is given by 1/4 power of this ratio of P total over sigma A. So that is and sigma is Stefan's constant. Okay, so that gives you the temperature to be 131 Kelvin approximately. So that this is where we kind of stop now. We have gone through several different examples we have visited one example where you have used the Wien's displacement law, then Rayleigh-Jeans limit, then again the Planck's law, and also the Stefan-Boltzmann law. From there, we'll take up some more examples in the following lecture, and we'll also put it up if you're confused. This brings us at close with the lecture number 3 for this particular week. I hope you liked it. If you have any questions, you can also write back to us, and we'll try to answer them. So good. I think we'll see you for the next lecture. Thank you for joining.